It's my honor today to present the Dean of Science, Jonathan Schaeffer, who will talk to us about artificial intelligence and games. Are we set to go technologically, everyone? Okay.
Okay, thank you very much, everyone. Can you hear me? Is the volume okay? I'm delighted to be here. Anytime I get to talk about something I'm passionate in is always a lot of fun. This is a general purpose talk. This is not a detailed technical talk. If you want technical, I'd love to talk about it. But what I've done today is put together a bunch of things that are more human interest. I know that you've had the talk, the singularity talk from a few weeks ago. My goodness, I don't know what the presentation was like, but there was a massive amount of information in that PowerPoint slide. So if you actually covered it all, I'm sure that it would be very difficult to absorb a lot of material. So I think that my approach is just to make something a lot of fun. So my area is artificial intelligence. I work on trying to take computer programs and make them do the kinds of things that you and I do every day. But I'm best known for working on games. When I was a young student, I had a fascination with games, and I thought they were cool and fun and be interesting to write programs to do games. And people said, you can't do games because it's not academically credible. If you're going to work in artificial intelligence, do things that will make a difference in the world. Write a program that will play doctor, or write a program to be judge and jury, or try and write a program that could be as good, you know, as the Prime Minister of Canada. You know, that was an easy problem. But come up with something challenging that could make a difference in the world. And you know what I said? You know, a medical program, like, I'd heard about some of these things like mycin and stuff like that, and I read the papers and they're all full of this jargon. I don't want to offend anybody, but yes, there's a lot of jargon in medicine. And it wasn't fun to me because my passion isn't doing medicine. My passion is playing games. So in the late 70s, I started working in games, and of course then it was like uncool. And until 1997, everything I did in research had nothing to do with games. But in fact, what I did is I did other things part-time which were academically credible to bring in the research money so that I could funnel it to work on games. And then in the late 90s, games became credible and popular, and I came out of the closet, so to speak, and now all my research grants are in games. So no more lying and deception. So I formed what we call the Games Research Group at the University of Alberta. Games, it's an acronym, you don't need to know what it is, but it's the largest group in the world doing research in computers and games. And we've worked on all sorts of classic games. That was my route. I was interested in the 1970s of writing a chess program. And we worked on checkers and Go and a variety of others. Board games like that, card games like poker, which are currently ongoing activity. And now an area which is much more interesting to me called general game playing. Can you build a computer program that's so general that it can play any game? You and I are general game players. I can give you a game, you'll read the rules, you'll figure it out, and you'll play the game. You may not play it well, but you'll do a creditable job. Can we come up with a computer program that could do that? And for the last 12 or so years, we've been working with commercial game companies, in particular BioWare and Electronic Arts. Obviously, games are multi-million sellers. You know, when I worked on my chess program in the 70s and 80s, there was exactly one user, me. And then my checkers program became famous, and I put it up on the web, and daily I would get hundreds of users, and that was kind of cool, hundreds of users. And then we did poker, which was really popular in the last decade, and we put it up on the web, and we had thousands of people using it. In fact, we had a commercial product that sold probably about 100,000 copies, and that was like, wow, 100,000, that's cool. And then we developed some technology for pathfinding that ends up in a BioWare game, and I'd like to think that the game was so fantastic because of that small piece of technology we put in, but the bottom line was the game sold many millions of copies. And so going from classic board games all the way up to commercial games, there's an economies of scale there. And so, you know, I've written a book, it sold a few thousand copies, but I've written some code that's appeared in a game that sold millions of copies. So, you know, maybe I can say I'm a best-selling author of millions of copies of something. So that's what we do, is we play games all day. It's called research, but we do play games. So what is AI? And this is an interesting question because I very quickly learned that you have to be careful using the word AI, especially when you're giving a talk, because AI means something to different groups of people, like Amnesty International, or the worst case was not knowing somebody was in agriculture in the room, and they assumed I was talking about artificially inseminating my opponent. So that was rather awkward. AI turns out to be actually a legal word. It is a three-toed sloth from South America. That's a picture of it. And they're very good at climbing trees, which is actually very interesting because computer game programs search through things called trees. So, what is artificial intelligence? It's the field of computing science that is trying to mimic what humans do. We consider ourselves the top of the food chain. With our intellectual capacity, we've been able to do amazing things. And the question is, can a computer do those same things? It turns out AI is such an all-encompassing field because when you start thinking about intelligence, there's more to intelligence than just the processing up here. It's the vision. The amount of information we're processing is unbelievable. Like right now when I'm looking out across this room and I see lights and a ceiling and desks and people and cameras and lights and everything, I'm processing that information instantly. And that's an incredibly complex computational task. And yet nature has seemed to evolve that capability. I'm talking to you. That's an impressive capability because in real time, I'm making up a speech. I'm saying things that I haven't said before in ways that I've never said before, and yet my mind in the background is processing it, and out comes something presumably that sounds reasonably coherent. At the same time, I'm waving my hands, and my brain is also controlling my heart and my lungs and all sorts of other capabilities. So, you know, we're talking about speech and vision and reasoning. And then we touch into other areas like robotics and language. What about learning capabilities, planning? There's so much that is encompassing in AI. It's really quite remarkable what the human and the human brain is capable of, and artificial intelligence is all about trying to mimic all of that. So it's a pretty daunting area. I like this slide because when we think about the computer revolution, we're missing the fact that it really is computer evolution. Because what we need to do is rethink what it means to think. Until recently, we thought thinking was something only for a living being, and in fact, many of the intellectual processes that we follow only for superior intellectual beings like humans. But you know, just 12 years ago, we had a milestone. It was the turn of the new decade, the new century, the new millennium, and yet people missed observing one of the most important insights in history. I don't know about you, but I saw all these top 10 lists, like what were the 10 most important events in the 1990s, the last decade, or what were the biggest scientific breakthroughs of the 1900s, or what were the greatest milestones of the last 1,000 years. And they all missed what I thought was the most incredible result. One of the most profound contributions of the 20th century is the realization that intelligent behavior can be realized by non-human, non-living information processing architecture. Okay? Look at this. It's a phone. Okay? I can drop it. It's hard. There's no moving parts inside. There's no DNA. There's no brain. There's just electrons swirling around through some silicon. And yet this box this hard thing, to an outsider, it looks like a rock. It can crush you at chess. Think about the profound nature, the realization that what we call a computer can do things that you and I thought only humans could do, or living things could do. And that is absolutely profound. Forget about the religious implications. But it's not just this. We have other types of black boxes that can do intelligent things. Things like quantum computers, or even DNA computing, all sorts of things. And that is tremendously profound, to know that there is something out there, non-living, non-DNA based, that can exhibit intelligent behavior. Unbelievable. Now, the problem we have is that AI, artificial intelligence, is a moving target. Because people will say, you know, your smartphone, it isn't really AI, it's not doing anything intelligent. But think about it. Let's go back 100 years. What if I gave you a black box and I said, wow, this box, it's going to correct your spelling. It's going to fix your grammar. 100 years ago, you would have said, oh my God, how could that black box fix my grammar? That's incredible. Dogs can't fix grammar. Trees can't fix grammar. But this black box can fix my grammar. I can type in an email message and it points out ruthlessly every single spelling mistake I make. People will be stunned. Obviously, this is an incredibly intelligent object. Spell checking is so boring, it's mundane today. Who cares? Yeah, we got spell checkers. It's not artificial intelligence anymore. It's a moving target because we've raised the bar. Go back 50 years ago, flying an airplane. Used to be all these daredevil stunt pilots. Go back 50 years ago when autopilots came on. There's computer programs, black boxes, non-human brains that are going to take that airplane and fly you thousands of kilometers around the world and land you safely. That's amazing. What does it take to fly a plane? For a human vision, extensive training, enormous skill, and yet a computer's doing the whole thing. But that's not AI anymore. 50 years ago, we would have said, wow, that's a massively intelligent machine that's flying the plane. And now it's not even AI. So we have this credibility problem. Once we understand something and we figured it out, the mystery is gone. It doesn't really require that much in the way of intelligence, and it disappears. It's no longer AI. So if you go back 100 years ago, this was AI, and 50 years ago, this much was AI, and what is AI today is this small little core piece, because it keeps shrinking. And as science keeps progressing, we understand more about what intelligence is. That piece that remains a mystery gets smaller. The more we learn about intelligence, the more we realize there's not a lot of magic in human intelligence, so far. So, what do we do in AI? So I argue that there's at least two different architectures for intelligence. So on the left you have the familiar biological model, the human brain. But on the right, we have this new model that was invented in the 20th century, the computer. It has silicon chips, it has disk drives, it has fans, it has a whole bunch of things. It's a completely different architecture. But for many problems, those two architectures are able to solve the same problem. They can both play chess. And we all know that playing chess requires some level of intellectual skill, and if you want to play it really well, presumably it requires high level of skill. So this is the hardware that we use for intelligence. And so there are two architectures, and there's others. I mean, quantum computing and DNA computing and other kinds of computing. Let's ignore them. Got two physical models for computing and exhibiting intelligence. And what's interesting is it shouldn't surprise you that because the architectures, the hardware is different, they have different strengths and different weaknesses. So humans are very good at asking things like how, why, what, where, and when. And computers are very good at sifting through possibilities. So if you think about a human, what are humans good at? They're good at vision, speech, writing plays, learning. What are computers good at? Memorizing 1 billion facts, computing third-order partial differential equations to 64 digits of accuracy, executing, doing something repetitiously 1 billion times. But what's interesting is that the two architectures are complementary. What humans are good at, computers are bad at, and vice versa. Are you going to ask a human, quick, in your head, I'm going to give you a third-order partial differential equation, and I want you to give me the answer to 64 bits of accuracy now? You can't do it. Okay, here's the Encyclopedia Britannica. I want you to memorize the whole encyclopedia now. You can't do it. All right, here's something I need done. I want you to execute this task 1 billion times. Well, you'll do it a few times. Maybe you'll even get up to 100, but you're going to get bored pretty quickly. You're never going to do it 1 billion. But all those things are easy for a computer. On the other hand, if I ask the computer to come up with, create a beautiful sonnet, something that's aesthetically pleasing, it'll have trouble. If I ask a computer to look at this entire room and immediately, instantaneously point out all sorts of subtle details, you and I can do it, it can't. If I ask the computer, I want to carry on an intelligent conversation with you about baseball, the hurricane, the US election, Stephen Harper's new pet, the Canadian dollar, I mean, the computer's going to have trouble coming up with a coherent conversation with me. So human strengths are computer weaknesses, computer strengths are human weaknesses. And what's interesting is when you get into artificial intelligence, and when you look at these two architectures, the human and the computer, if I'm going to solve a problem using a computer, I'm going to play to the strengths of the computer, not the weaknesses. Just like a human, if I ask you to solve a problem, you're going to do what you do well, and you're going to play to your strengths. If I asked you to do something and said, here's solution A, which involves understanding a few principles, here's solution B, which requires memorizing 1 billion facts, which one are you going to choose? You're obviously going to play to your strengths. So when you look under the hood of a computer and see what's actually going on, you may actually be very disappointed, because even though you think it's exhibiting intelligent behavior, what it's actually doing may be, in fact, quite stupid. And so some people say, you know, is this a paradox? The program can play really good chess, but when you understand what it's doing when it plays chess, you say, that's really dumb. How can dumb things give rise to intelligent behavior? Is it a paradox? And I would argue it isn't a paradox. It really goes back to the question, a fundamental question is, what is intelligence? And that's a very deep philosophical question. So let's take a look. Can you see this video very well? From here it looks dark. I don't know if there's too much light here. If you guys can see it fine, then I'm okay. Let me give you an example. This is Garry Kasparov, who was world chess champion, and in 1997 he played the chess machine Deep Blue. And let me show you a video of this. Let me give you a bit of a prelude just to show it. Kasparov played the predecessor of Deep Blue in 1989 and crushed it. Kasparov played Deep Blue in 1996 and won the match. And in 1997 he was pretty cocky and confident he was going to win the match. And here's what happened. In game one, it was a draw until very late in the game. A bug showed up in Deep Blue, and Deep Blue made a random move. Yeah, a truly random move, and lost. Kasparov won game one. Game two, Deep Blue played brilliantly, unbelievably brilliantly, a game that anybody, any grandmaster would be proud of. And at the very end of the game, in a trivial winning position, Deep Blue made the obvious move, and it turns out in that position there's a flaw, some miracle that nobody saw at the time that would allow Kasparov to have escaped with an unbelievable draw. Nobody saw it, Kasparov didn't saw it, and he resigned. And so Deep Blue won the game, and it was only a few days later that people realized there was this Hail Mary pass at the end of the game that would have saved Kasparov. So Deep Blue won it. The next 3 games were draws, and in the last game of the match, Game 6, Garry Kasparov played like an idiot and got crushed and lost. Here's a video clip of the press conference where you'll see Garry Kasparov resigning the last game. And then he goes and you can see him at the press conference, and he's pretty flustered and he's making up excuses, but he does say some interesting things. One of the things I'd like you to watch when you see the video, actually I don't know, do I have a pointer? Okay, no pointer. When you look at the video, you're going to see Kasparov pointing to a table where there's 5 people seated at the table, and they don't say anything. But I made a note, I think the 5th person from the left, you can just take a look at that person and we'll discuss it in a moment. Just a sec, okay.
As long as I could keep under pressure, you know, forget today game. I mean, Deep Blue hasn't won a single game out of 5 because, again, game 2 I resigned when I could force a draw. Now, force a draw. Now, if somebody has another opinion, stand up and tell that the position was not a draw. Game 2 was resigned in a completely drawing position. Is it the correct statement? No, is it the correct? No, I just want, no, it's important. Is it the correct statement, Mr. Benjamin? Game 2. Final position was draw. Now, very important. Now it was recognized that Deep Blue made a bad mistake in a completely winning strategical position, blundered a perpetual check.
So I found this really embarrassing and offensive, and I was in the audience that day and I was really, really angry. First of all, he doesn't mention that game 1 was a draw and Deep Blue made a mistake, so he got a lucky win in game 1. But, you know, he points out in game 2, it wasn't really a win for the computer because, like, I could have drawn. Like, okay. And at the beginning, he talked about game 6, the one he just resigned, which didn't count, right? And so, like, Garry, you lost 2 games to 1, and you don't mention the game that you won, which was a fluke. And the 2 games that you lost, we shouldn't count. So, like, what kind of logic is that? Anyway, it shows one of the weaknesses of humans. We have emotion. Computers are unemotional. I did show you that that table. The person who was first on the end, you probably don't know that person. His name was Ken Thompson. He is the inventor of the Unix operating system, very well known in computer circles. Unix became, well, evolved into things like Linux. The person 5th from the left, his name is Murray Campbell, born and raised in Edmonton. His mother's still here, did his bachelor's degree at the University of Alberta, bachelor's and master's degree at University of Alberta before going to Carnegie Mellon and doing a PhD. Murray is one of the 3 co-authors of Deep Blue, so you saw the other 3 authors there. And so U of A has a very long history in computer games, and particularly in computer chess. Murray Campbell, one of our distinguished alumni, is one of the authors of Deep Blue. So here's what happened in 1997, man versus machine. This is like the boxing scorecard. Deep Blue was a little taller than Garry Kasparov, 6'5" versus 5'10". But they had a big difference when it came to weight. Garry Kasparov loved to play tennis and exercised a lot. He was 176 pounds, very trim, muscular man. Deep Blue was kind of portly, looked like a refrigerator, and because of the amount of fans inside, was kind of cool like a refrigerator, but a big box weighing a hefty 2,400 pounds. At the time of the match, Garry Kasparov was 34 years old. Deep Blue, the hardware, the body of this chess-playing machine, this chess-playing intelligence, was a half a year old. So a toddler beat Garry Kasparov. I should point out that whereas the physical hardware was only a half-year-old, the software, the intelligence, had been evolving for 10 years. This is one of the magic of a computer. You can develop the intelligence on one machine and move it over to another. Clearly, when I hit 34 years old one day, I would be very appreciative if we could just take my brain and move it into a teenager's body. That sounds really attractive. Garry Kasparov, in his brain, has computers. They're called neurons, but they are computers. He has about 50 billion of them. They're very simple computers, but they are computers. 50 billion neurons. Deep Blue, on the other hand, had a pathetic 512. That's it. 512 computers. Kasparov was crushing him. He had like a millionfold, whatever it is, advantage in terms of number of computers. On the other hand, though, there's a little bit of a difference in speed. With all his massive computing power, Garry Kasparov, and this is typical of humans, can only analyze about 1 or 2 chess positions per second. That's it. Our brain has enormous capability, but it's slow. 1 to 2 positions per second. On the other hand, Deep Blue was analyzing 200 million chess positions per second. In fact, it had the capability of doing 1 billion positions per second, but the software wasn't sophisticated enough to do it. But 200 million chess positions a second. The only reason Garry Kasparov was in the game, so to speak, was because he had extensive knowledge about chess. And Deep Blue's knowledge is extremely primitive, rudimentary. It's the kind of knowledge you could give to a beginner chess player. They both had electrical power sources. Garry Kasparov, as you probably could have gathered from the video, had an enormous ego. Garry Kasparov probably needs his ego to be a competitive world champion. Deep Blue, of course, was extremely modest. It didn't even blush at all those rude comments that Garry Kasparov was saying about it. It has no ego. On the other hand, I can tell you that the programmers of Deep Blue do have enormous egos. My point here is that you can see computers today are superhuman at chess. They can crush humans, even the best in the world. And when you look at this diagram, you can see that we're taking an approach that matches well with what a computer can do, not what a human can do. The computer is very good at looking 200 million chess positions per second. We've designed algorithms that exploit the strengths of the computer, not the weakness. So the computer solving method is completely different than that of the human. Here's another example of this difference. People like crossword puzzles. I like crossword puzzles. Every weekend there's the New York Times crossword puzzle. The Sunday, the weekend crossword puzzle is like, what is it, a 20 by 20 grid, something like that. It's tough. And I have, if I fill in 15, 20% of the answers, I'm doing well. So, obviously I'm pretty stupid because there's a crossword puzzle, there's the clues, I can read the clues. Most of the time I can't figure out the answer, and most of the puzzle I leave empty. On the other hand, in the late 1990s, Michael Lippmann, then at Duke University, built a crossword puzzle solving program. First thing he did is he said, I'm going to build a database of all the previous New York Times, LA Times, other big popular crosswords. Just build a database of all the questions and answers that have been used in those puzzles. And you know what? His program scores 34% of the answers just by looking things up in his database. I, with all my intelligence, get 10 to 15% correct, and just him memorizing all the previous puzzles can score 34%. Okay, so obviously I need to have a better memory. He then added in some specialized solvers and internet searches. So this is what he did. It was really dumb. We'll say there's a clue like, what is the capital of Alberta? And he'll go to the puzzle and he'll say, well, 8 letters. So he says, okay, capital of Alberta. I'm going to do a web search. I'm going to go to the Internet Movie Database, and I'm going to say, find me 8-letter words that have something to do with Alberta in the Internet Movie Database. And it's probably not going to find many pages with Alberta, and it'll find some, and then it'll pull out all the 8-letter words. And then it'll go to a medical site and do the same thing. Probably won't get any hits. And then it'll go to a history site, and it might get a whole bunch of hits. And then it'll go to a geography database, or choose your favorite database. It did about 14 web searches. And then it got all the statistics back. And guess what? What word comes out the most often? It's Edmonton. Well, it's not a guarantee that Edmonton's the answer, but Edmonton was the top hit, and it's 8 letters. Well, I'm going to put it into my puzzle. You know what pisses me off? Excuse me. I understand the clue. It said, what is the capital of Alberta? I know what Alberta is. I know what it means to ask what is the capital of Alberta. And I happen to know that answer, and I'll get it. But it could say, what is the capital of Nigeria. I have no idea. But I know what it's asking, and I understand the question. Michael Littman's program doesn't understand the questions. It just takes the words in the question, throws them into an internet search engine, gathers statistics as to what the most popular answer is with the right number of letters, and plugs that into the puzzle. And it beats the pants off me. I understand the clues, and I can't compete with it. And so what we've discovered is that information retrieval without understanding the information is a powerful technique. You and I would never do that, but to a computer, it's amazing. And we know this. We do it with Google, right? You put in a few keywords and bang, your top hit usually gives you the answer that you want. What's so sad about this is with all my efforts and all my 29 years worth of experience, I can only score 10 to 15% on the New York Times crossword puzzle. Michael Littman's program, building a database of previous puzzles and doing dumb, blind internet searches, scores 97%. It's a different way of doing it, and obviously it's much more effective than me. So what is my definition of what I do in artificial intelligence? I'm not creating intelligence. I'm not going to pretend to do and get into the religious world, God creates intelligence. I'm not going to touch that. But what I do is I believe that what my field does is create the illusion of intelligent behavior. Is a program that plays chess by searching 200 million chess positions per second intelligent? It exhibits intelligent behavior, but what's underneath there is actually fairly rudimentary. And it's a purely mechanical procedure. You could follow the exact same procedure and you would play grandmaster chess. You just wouldn't have the patience to do it. And it'd take your lifetime to do it because you're not fast enough. Are you going to memorize every single New York Times crossword puzzle? No. Am I creating intelligence? No. But by memorizing a whole bunch of things and doing dumb internet searches, I can create the illusion that I have a smart program. And so that's what I do. But there is artificial intelligence. I should point out that we do have artificial stupidity as well, and some humans do try to create the illusion of intelligence as well. All right, so now what I want to do is just talk about, with my interesting games, a bunch of things that are games related or games researcher related to illustrate what's going on these days. So, what's the most visible AI when it comes to games? What is the most visible AI, first of all, period? And the answer is computer games, by far. There's lots of applications of artificial intelligence, but the one that everybody relates to is computer games, because most computer games have artificial intelligence inside. And there's lots of challenges there, because we want to create in these games characters that exhibit realistic behavior. I mean, if you have a character that just walks into a wall, that looks stupid. It could be fun and entertaining, you'll have a good laugh, but it is stupid. You want to have realistic behavior, so it's a big challenge. You also want to have realistic conversations in these games. Most games don't have it. They have pretty canned conversations. We want to have real-time decision-making. You want computers that can play these games and make decisions, let's say strategy games, immediately at the same kind of pace that we can. And they have to do planning. Lots of different things, different challenges in computer games. That is by far the most visible AI. And the game that's had the most interest, most of you have probably never heard of it or ever played it, is a game called Facade. It's probably 10 years old now. But it's the first game where people actually built an emotional bond to. You can play games and you're attached to the game. You can play Warcraft, and many people do, 50 hours a week, and you have an affinity to the game, but not emotionally, other than perhaps your competitive spirit. But this was an artificial intelligence project, and it was the first game where people had strong emotional responses, where people actually could play a game and for example, could cry. That's one of the holy grails, is computers to do things that would evoke emotional responses like crying. And this was a very clever game. It's all about a couple, and you are visiting them, And as the game goes on and decisions you make lead to different scenarios, but it turns out to be a very awkward situation where the two couple, the husband and wife, are obviously having marital difficulties, and in some such situations there's fights, and there's all sorts of awkward situations that I suspect any married couple would relate to, and it's quite engrossing. Many novel techniques in that game. But we still have a long way to go. So here's a video, and I'll provide some comment. This is about 5 years old now, 6 years old, the game Oblivion, which at the time claimed to have world-class AI, but I'll let you be the judge of that. Now this guy is going to have to go to a room and he's going to try and retrieve something.
Well met.
You notice, just walked right through the person.
Hello.
Hello.
What's new with you?
I heard people saying they ran into goblins around here not long ago. I can't stand those things.
Goblins. Evil, foul-smelling little brutes.
So watch the intelligence here. The characters. She's going to try and get attention. So I jump on the desk. No reaction. Kicked over the cup. No reaction. No reaction. No reaction. But I'm going to pick up the feather.
Somebody help! Come quickly! We've got a burglar! Stop! Thief!
Stop right there, criminal scum! Nobody breaks the law on my watch. I'm confiscating your stolen goods. Now pay your fine, or it's off to jail.
And of course, I'm not going to pay the fine.
Then pay with your blood! Am I supposed to be impressed?
And of course, I'm a coward, so I'm going to run.
Watch out!
Watch the spectator. Just standing there as the sword goes through him as he's blindly just sitting there.
Pay the fine!
So you can see there's just enormous amounts of unrealistic behavior in there. And the holy grail is to make this as realistic as possible. Realistic conversations, not canned. You know, having the guy walk in front of the sword and the sword going through him just doesn't make sense. But sadly, these are problems that we still need to work on.